This glass breaks. The soul that occurs shadows round my feet. And my hands, they bleed. The sting now I always remember. A sting stays in me. But this changes you. It's falling down and breaking. Now she knows it's never right for me to say I wanted this. I know I could still go. I gave it all. Give it up on lock, my hands up all the doors. This love you broke can close it all and don't forget to fade. A smile you had. You tried so hard to fool yourself instead. You give it your hands on the door. You gave it Sweet December's coming round. City's people have fun. You're the truest thing in this town, and I want you now. Shadows from the streetlight shades, watching every word you say. Never seen you look like, and I want you now. All your love in an old regard card, and I want you now. Spinning like a turning wheel, looking like the way I feel. You can keep all that you steal, 'cause I want you now. Nothing more than nothing more than
Yes. Do you want to know where to invest $1,000 right now? Well, forget about AI, quantum computing, electric.
The universe is teeming with galaxies, many bigger, brighter, and more densely packed with stars than the Milky Way. But most are so inconceivably far away that they are much too faint to be seen with the naked eye. However, there is one galaxy which appears visible in the night sky, a galaxy that has revealed to us as much about the universe as it has about itself. That galaxy is the Andromeda Galaxy, a vast, ancient colony of stars, more than twice the size of the Milky Way. Today, we will be taking a journey from this galaxy's ancient history right up to its remote future, using the most beautiful images and intricate data to know our cosmic neighbor like never before. This is our journey to the Andromeda Galaxy. The Andromeda Galaxy is known by many names. This one owes to the constellation in which it can be found, named after the Phoenician princess Andromeda, wife of Perseus in Greek mythology. It is also known as NGC 224 and Messier 31, according to the various star catalogues it has appeared in. Unlike most galaxies, Andromeda is visible to the naked eye, best seen in dark, moonless skies during autumn and winter nights in the Northern Hemisphere. As such, it was discovered long before we knew that other galaxies existed, but it was incorrectly assumed to be a nebula residing within the bounds of the Milky Way for the longest time. The earliest known mention of the galaxy came in the year 964 AD, in Persian philosopher Abd al-Rahman al-Sufi's Book of Fixed Stars, which recorded it as a nebulous smear. But it wasn't studied in any greater detail until the invention of the telescope in the early 1600s, when it was rediscovered by Simon Marius. Later, in 1764, the object was added as the 31st entry in Charles Messier's catalogue of deep sky fuzzy objects, which included a number of other galaxies, unbeknown to Messier himself. Later that century, William Herschel noticed that the centre of M31 appeared to have a red tinge when compared with the exterior, and because he was able to observe such fine detail, he incorrectly assumed Andromeda to be the nearest of all the great nebulae, postulating a distance of no more than 18,000 light-years. In 1845, William Parsons was the first to identify a spiral structure in the galaxies M51 and M99, and 5 years later, he added Andromeda, along with these galaxies and a number of others, to a new classification of so-called spiral nebulae, believing them to be their own type of gaseous cloud within the Milky Way. However, not everybody was convinced by the nebula explanation. A few well-respected minds of the time, starting with 18th century philosopher Immanuel Kant, suggested that this object may in fact be its own island universe. A vast congregation of stars like the Milky Way, but situated much further beyond than any other object. Back then, however, the Milky Way was thought to comprise the entirety of the universe, and this idea placed M31's distance on a scale much too vast for contemporary astronomers to accept. That was until 1917, when American astronomer Heber Curtis witnessed a nova event coming from inside M31, where a transient luminous object briefly outshone its surroundings. After scouring the limited collection of historical photographs of the object, Curtis found no fewer than 11 other nova events occurring inside Andromeda, considerably more than anywhere else in the Milky Way, but all appearing to be around 10 magnitudes fainter than those observed elsewhere in the sky. It was at this moment that Curtis realized what he was looking at. Not a nebula, but a much more distant and remote colony of stars like the Milky Way. This led Curtis to revive Immanuel Kant's island universe hypothesis, proposing Andromeda to be some 500,000 light-years away. But this claim was disputed by many scientists, most notably by fellow American astronomer Harlow Shapley, who had previously measured the Milky Way, and thus what he considered to be the entire universe, to be around 300,000 light-years in diameter. This culminated in one of the most significant events in 20th century science, the Great Debate of 1920, where Shapley and Curtis discussed the nature of the universe and of the spiral nebulae in front of a live audience at the Smithsonian Museum of Natural History. Shapley, on the one hand, argued that the Milky Way was the entire universe, and that all known spiral objects were merely their own type of nebula residing within. He argued that, if they truly were other galaxies, their distance would have to be in the order of tens of millions of light-years, a jump in scale not many contemporary astronomers were willing to accept. Curtis, on the other hand, highlighted the overdensity of novae within Andromeda when compared with the rest of the Milky Way. He argued that no type of nebula could explain the high number, yet consistent dimness of these events. He also pointed out dark lanes within early photographs of Andromeda's spirals, noting their similarities to the opaque dust clouds lying within the Milky Way's zone of avoidance. But the debate ultimately yielded no clear winner, and it took another 4 years for the question to finally be put to bed. In 1924, Edwin Hubble settled the debate by using the Hooker telescope in California to measure pulsating Cepheid variable stars within Andromeda. A variable star's pulsation period is indicative of its luminosity, and once we know a star's luminosity, we can compare that to its apparent brightness from Earth to constrain a distance. Using this technique, Hubble indisputably demonstrated that M31 was more than 1 million light-years away, and thus had to be its own galaxy. Furthermore, all the so-called spiral nebulae that had been discovered were their own galaxies as well. each lying tens of millions of light years beyond our local group. The true, terrifying scale of the universe had been revealed, a universe filled with thousands, or perhaps even millions of galaxies, a scale far beyond anything thought possible before. Once we had realized that M31 was a separate galaxy, our understanding of the universe took a great leap forward. Thanks to its proximity, Andromeda offers an unparalleled opportunity to study a spiral galaxy like the Milky Way from the outside looking in. By the 1950s, we were making radial maps of the galaxy, and today, all 4 of NASA's great space observatories regularly survey Andromeda for ultraviolet, infrared, and X-ray signals. And while there hasn't been a dedicated spacecraft or mission to study our neighbour, there have been a number of telescopes launched to survey more distant galaxies. And for telescopes like Hubble, which regularly stares at galaxies billions of light years into the void, a galaxy under 3 million light years away is a simple task. And thus, we have a wide range of beautifully detailed and jaw-dropping images of Andromeda. We have made mosaics of its stars and maps of its interior. We've found clusters, clouds, neutron stars, and black holes within its bounds. Its interior content mirrors that of our own galaxy, but often on a larger scale. And so, without further ado, let us dive into these findings as we set out on the road to Andromeda.
Who's got one out there?
Outdoorsy stuff is not my thing. I played an indoor sport for a reason. Hopefully that's where I heard it. It's all kinds of nice. I'm Sue Bird. I'm a retired professional basketball player, and so
Andromeda is a barred spiral galaxy, like the Milky Way, consisting of an outlying spiral structure of dust and gas, connected by a dense bar-shaped concentration of stars in the galactic core. Our neighbour's structural similarities to our own galaxy suggest that the two followed similar evolutionary paths. Andromeda is thought to have formed around 10 billion years ago, and has been growing by crashing into and consuming other galaxies ever since. M31's torrid past is evidenced by its vastly elongated structure. The visible component of the galaxy is thought to be around 120,000 light-years in diameter, not too dissimilar to the Milky Way. However, Andromeda's full structure includes an extended disk of scattered stars flung outwards by tidal interactions, giving the galaxy a maximum extension of some 220,000 light-years, by far the largest object in the local group. Its stellar population greatly outnumbers even the most generous estimates for the Milky Ways, with M31 thought to be home to more than 1 trillion stars. The galaxy's distance from Earth has been constrained via a number of different methods, with most measurements agreeing on a value of about 2.56 million light-years. The first step in this enormous, expansive journey comes when we rise above the plane of the Milky Way. As less of its starlight extinguishes our view of the galaxies beyond the local group, the true mind-blowing scale of this enormous universe becomes apparent. Once we have passed beyond the Milky Way's outlying stars and its ghostly satellite galaxies, we reach intergalactic space, just about as empty as you can get in a universe dominated by gravity. For comparison, the air we breathe on Earth contains approximately 10 trillion atoms per cubic meter. Even just above the atmosphere in space, there are still 1 million trillion atoms per cubic meter. Interstellar space between stars only contains around 1,000 atoms per cubic meter. But in intergalactic space, that count drops to just 10 atoms per cubic meter. But with that said, there's not nothing out there. The Great Galactic Highway also contains the most ill-fated stars and planetary systems, which have been ejected from their galaxy entirely by the enormous tidal forces of collisions. The conditions on such worlds are just about as cold and as lonely as you can get in space. With no heat source of any kind, out here, intergalactic rogue planets freeze solid, from their atmospheres right down to their cores. Only halfway into our cosmic journey do we begin to stray into Andromeda's territory, not yet into its starry fields, but instead into its enormous galactic atmosphere. Like the Milky Way, surrounding Andromeda is a diffuse halo of plasma, thought to have been expelled with tremendous force by reverberations from Andromeda's past collisions. This gives the halo a truly staggering radius of 1.3 million light-years, extending more than half the distance between M31 and us. Inside this atmosphere, we find Andromeda's satellite galaxies, each hiding clues about its violent past. Andromeda currently hosts more than 20 known satellite galaxies, and probably had more in its past, which it has since devoured. Of these satellite galaxies, there are 3 in particular which are thought to have played a key role in forming Andromeda's skewed, elongated structure and its enormous galactic halo. They are Messier 32, Messier 110, and Messier 33, aka the Triangulum Galaxy. M32 is a small dwarf elliptical galaxy, seen as a little fuzzy blob of golden light in close-up photographs of Andromeda. The satellite is only around 6,500 light-years in diameter, yet it is held together by a supermassive black hole, more than 1 million times the mass of the Sun. That is an extremely massive nucleus for such a small galaxy, which suggests that it may have been larger in the past. Given the mass of the central black hole, scientists think that M32 may have once been its own spiral or lenticular galaxy, even larger than the Triangulum Galaxy, but ultimately not large enough to survive its encounter with its host. As the 2 galaxies came within touching distance of one another, the ill-fated proto-galaxy had its outlying stars absorbed by Andromeda, leaving only the dense galactic core bound to the supermassive black hole. Now it appears as a small golden elliptical galaxy with an aging stellar population. M110 is another elliptical satellite galaxy of Andromeda, larger than M32 at around 17,000 light-years in diameter. Much like the former, M110 is thought to have interacted with Andromeda in the past. Scientists have detected faint, dusty, metal-rich lanes within Andromeda's halo, thought to be made up of stars stripped from the satellite galaxy as it came within reach of Andromeda. Imagine what it would be like to live inside M110. You would see Andromeda's vast, side-on galactic disk consume your sky at night. Just think of the historical, societal, and religious implications if early humans had seen something like this hanging in their ancient sky. Finally, there's Messier 33, aka the Triangulum Galaxy. It is the current 3rd largest member of the local group, a dwarf spiral galaxy around 60,000 light-years in diameter. It is not known whether M33 is a true satellite of Andromeda. It may just be its own galaxy, which happens to be situated around 750,000 light-years beyond. But in any case, the 2 galaxies have definitely interacted within the last few billion years, and the data points to them interacting again in the future. with the 40 billion stars of the Triangulum galaxy destined either to be absorbed into a new galaxy or to be banished out of the local group entirely.
Are you struggling in your calculus class? Do you have a hard time understanding your instructor? Do you wish there was a simpler way? I get it. It's frustrating. You go to class expecting answers only to walk away with more questions. You get your teacher.
Finally, after millions of light years on this dark, lonely voyage, we arrive at the Andromeda Galaxy's outer edge. Once we've passed through the plasma halo, we reach the denser, extended stellar disk, made up of stars scattered by Andromeda's past collisions. Once we're through all of that, we finally reach the visible component of the galaxy, the barred spiral structure, rich in dust, gas, and metals, similar to the Milky Way. But unlike the Milky Way, Andromeda's spiral structure is more complicated, having been deformed by billions of years of gravitational interactions with the likes of the Triangulum galaxy, among others. In 1998, the ESA's infrared telescope suggested that Andromeda may be transitioning into a ring galaxy, as the dust in its body appears to be grouped into overlapping rings at various distances from the core. Studies in the years since, using NASA's Spitzer telescope, have shown two spiral arms which extend away from the central bar and beyond the rings, but they are fractured into 7 spiral segments, separated by junctions of enhanced hydrogen gas, where vigorous star formation is occurring. NGC 206 is one such region, Andromeda's largest star-forming cloud, situated at a boundary between two of its southwest spiral arms. At around 4,000 light-years in diameter, it is one of the largest clouds of its kind in the entire local group, and contains a cluster of more than 300 luminous blue supergiant stars with diameters dozens of times that of the Sun. And NGC 206 is not the only place where we find clusters in Andromeda. In fact, we've identified more than 460 globular clusters within its bounds, more than treble the number discovered in our own galaxy. The most significant of these clusters is Male 2. It is Andromeda's most massive known cluster, containing several million luminous stars of varying ages and metallicities. The mass, luminosity, and overall disparity in its stellar population implies that Male 2 may not be a true globular cluster, and may actually be the disrupted heart of a proto-galaxy. In a manner similar to M32, but on a smaller scale, the outer layers of Male 2 were stripped away and dissolved into the fields of Andromeda, but its galactic core managed to remain bound by its central intermediate mass black hole of 20,000 solar masses. And so now, these surviving stars cling to the black hole as it barrels around the galaxy, appearing as a surrogate globular cluster which hides the secrets of a richer past. Andromeda's stellar population seems broadly in line with the Milky Way's, containing old and young stars, clusters, nebulae, black holes, and perhaps life-supporting worlds around stars like the Sun. Unfortunately, M31 is much too distant for us to be able to hone in on the planetary systems of its stars. We can't even do that within our own galaxy. However, despite the odds, in 1999, scientists thought that they had detected indirect evidence for a planet within Andromeda, when a microlensing event was detected. Microlensing occurs when the light of a luminous source is bent very slightly as it travels towards Earth by the gravity of a planetary mass object. One possible explanation for this Andromeda-based microlensing signal, dubbed PA99N2, was that the light of a red giant star was being warped by a surrounding exoplanet with a mass 6 times that of Jupiter. Unfortunately, however, Microlensing events often occur due to unpredictable chance alignments, and so it's unlikely that we'll ever be able to catch this same signal again to follow up on it. But even if not the result of an exoplanet, we can still say with relative certainty that Andromeda, like the Milky Way, is home to billions of planets orbiting its stars, many of which will be Sun-like and suitable for supporting Earth-like worlds. In addition to live stars, we've also found dead ones within Andromeda. Our search for X-ray sources within our neighbour has led to the discovery of dozens of black hole candidates, and possibly even neutron stars too. M31 is likely to be crawling with these deceased stellar cores, left behind by its older generations of stars. But the most significant black hole is, of course, the one that lies at the centre of the galaxy, in the place where we find one of Andromeda's most peculiar features. Its dense galactic core is split into two regions, classed as a double nucleus, with the two nuclei dubbed P1 and P2. P1 is the more luminous concentration of matter, but it is offset from the centre, thought to be a blanket of bright stars orbiting the inner nucleus. In contrast, the less luminous concentration P2 does lie at the centre, and contains Andromeda's supermassive black hole, which powers its galactic tide. The black hole is estimated to be more than 100 million times the mass of the Sun, significantly more massive than the Milky Way's central supermassive black hole, Sagittarius A star, which is only around 4 million solar masses. The reason for this disparity, like so many of Andromeda's other features, is likely the product of its past collisions. As Andromeda has swallowed other galaxies, these mergers have supplemented its central black hole with abundances of gas and matter. Thus, M31's black hole has consumed much more mass than Sagittarius A star over the course of its life, culminating in this overwhelmingly large beast, housed by the fractured compound galactic core.
Why is Amazon paying me $63,000 a month? Well, I didn't make this kind of money selling yoga mats and toasters, and I damn sure wasn't talking my friends into buying vitamins and juices. I did it with a free app that's probably already on your phone, and that app is the Kindle app.
The journey to Andromeda is long, and at present untraversable for us humans. Even if we were able to escape the Milky Way's gravity, the time required to travel even one light year would vastly exceed the span of one lifetime. However, though we may not be able to get to Andromeda, we may not need to after all, as within a few billion years, Andromeda will come to us. When studying images of the galaxy, one striking aspect of Andromeda is its bluish tinge, but this is not the result of the natural colour of the galaxy's starlight. It is, in fact, being caused by a phenomenon known as blue shift, one of two types of Doppler shift. Doppler shift occurs when waves travelling towards an observer are warped by the motion of the object emitting them. Think ambulances and police car sirens. They sound different when approaching us to when they are moving away. This is because the oncoming sound waves are bunched up, while the ones trailing are stretched out. The same phenomenon applies to light travelling through space. If an object is moving away from us, its light will be shifted towards the red end of the spectrum, and the galaxy will become redshifted. Most galaxies in space are redshifted because the expansion of the universe is pushing them away over time. But by the same token, an object moving through space towards us will have its light waves compressed, causing them to appear blue. What this means is that Andromeda's aesthetic blue tint is indicative that it is heading right for us, at speeds of around 110 kilometers per second. The reason? Well, whilst the expansion of the universe separates most galaxies, Andromeda and the rest of the local group are all close enough to us to be attracted to the Milky Way's gravity. Thus, over the next several billion years, the contents of the local group will coalesce into a single object, starting with the head-on collision of the Milky Way and Andromeda. In the next 2 billion years, Andromeda will grow subtly in the night sky, creeping up in size until it becomes larger and brighter than the Moon and every other night sky object. Within 3 billion years, it will occupy a considerable portion of our field of view, its light and gas extinguishing the view of the universe behind. Of course, barring some sort of miraculous engineering, the Earth will have long been rendered uninhabitable by the evolution of the Sun. But should anything further out in the solar system manage to survive this far into the future, they will see their sky tarnished and illuminated by a messy, asymmetric galaxy collision. In 4 billion years, the two galaxies will have crashed into each other, fundamentally deforming their spiral structures and scattering their gases. After the initial impact, the cores of the two galaxies will be brought back round again and again until they merge at the centre. With each iteration, hundreds of billions of stars will be rippled by gravity and sent cascading in all directions. Yet, despite the sheer quantity of stars involved, it's statistically unlikely that any two will actually collide, as the space between stars is incomparably larger than the stars themselves. That being said, stars will pass within range of one another, wreaking havoc on the orbits of their finely balanced planetary systems. The fate of the solar system ultimately depends on its position during and after the merger. Scientists have run scores of simulations to ascertain a final resting place for the Sun, but there's no clear consensus. On the one hand, the solar system could be ejected considerably further out, maybe into the bounds of Andromeda, or perhaps even kicked into intergalactic space altogether. Alternatively, the Sun may be flung inwards, towards the torrid heart of the new galaxy, where it may be ripped to shreds as it comes within range of the core. Around 7 billion years from now, the merger event will complete with the combining of each galaxy's nucleus, i.e., when its two black holes collide. These supermassive black holes will gradually begin to orbit one another. As they use their dynamic energy to catapult stars out of their way, their orbits will decay and they will sink towards the centre. When they come within 1 light year of each other, they will start losing energy in the form of gravitational waves, generating immense tidal ripples which will be felt for billions of light years across space. Ultimately, these two black holes will merge at the centre, creating a new supermassive black hole which binds the heart of the new galaxy. And after this, the final phase of the local group's evolution will have commenced. A new supergiant elliptical galaxy, unoriginally named Milkomeda. Galaxy collisions like this one are commonplace throughout the universe, and have played an important role in forming rich, diverse spiral galaxies suitable for habitable worlds like our own. But this cycle of collisions and mergers has a limit, and once the elliptical galaxy has taken shape, it will not change its morphology much from there. Instead, it will gradually absorb the remainder of its satellite galaxies over billions of years, including the Triangulum galaxy, which will likely orbit the new galaxy in the meantime. It will take more than 150 billion years before the last members of the local group have been consumed by this monster galaxy. But once they have, that will be it, forever. Long before that happens, star-forming gases within Andromeda and the Milky Way will be exhausted, and less will remain for Milkomeda to repopulate its stars when it finally forms. Thus, while the elliptical galaxy is projected to undergo a productive starburst phase of vigorous star formation, this phase will be brief and less fruitful than those we've seen in other elliptical galaxies. With no new stars to accompany old ones, the general stellar population of Milkomeda will age, an ever-increasing share of its stars progressing into the red giant phase, where they will either explode or evolve into white dwarfs. As this happens, the expansion of the universe will speed up, pushing galaxies beyond the local group far out of reach, ultimately destined to become undetectable. We will never encounter or even see another large galaxy again, and save for a few small minor mergers within the local group's remaining dwarf galaxies, Milkomeda will run out of rejuvenation mechanisms to keep itself replenished. The galaxy will stagnate and will start to die out. It will happen incredibly slowly, over tens of quadrillions of years in fact. But the galaxy's stars will eventually cool to a temperature of just 5 Kelvin, at which point they will no longer be hot enough to keep themselves luminous, and they will freeze into solid, impenetrable spheres of matter, their life-giving elements locked away inside. Bit by bit, our galaxy will become darker and dimmer, and once the last star has faded away, the story of Andromeda and the Milky Way will be over. Thankfully, humanity was born in the middle of this great galactic story, long after its chaotic opening and long before its eternal depressing ending. Andromeda's story is more intertwined with the Milky Way's than the likes of Al-Sufi, Curtis, Shapley and Hubble could ever have imagined. And given that it's only been around 100 years since we realised that M31 was another galaxy, imagine what incredible knowledge our descendants will uncover in the next century.
Mom's great news. There's a body wash made with a gentle formula that's also affordable. Try Ivory.
And lift off.
Décollage.
The Milky Way is surrounded by more than 50 near-neighbour galaxies that make up the local group. Most of these are small, immature and relatively insignificant dwarf galaxies, with the two largest being us and Andromeda. The Milky Way is surrounded by more than 50 near-neighbour galaxies that make up the local group.
The universe is full of both verified and hypothesized objects that do not fit neatly into the humdrum world of standard classes of planets, moons, galaxies, and well-understood phenomena. So here are 10 bizarre deep space astronomical objects that have either been discovered or may well exist out there somewhere amongst the stars. Number 10, moons. One of the most common questions I get is, can a moon have its own moon? And the answer is yes, or so it's thought. While no example of this kind of object has ever been discovered, it's one of those instances in astronomy that seems likely to eventually happen. It's the concept of a subsatellite, or moon, where a moon of a planet has a moon of its own. While in most cases this isn't likely to occur in a planetary system, there are situations where it can. And indeed, we ourselves have created artificial moons in orbit of our own moon, though doing so is tricky. There are, however, natural candidates for this. Saturn's moon Iapetus has a very pronounced, unusual ridge extending around it that may have been caused by a past moon. But even stranger is the case of Saturn's moon Rhea. Last year, what appears to be a ring system was discovered around this moon, creating the odd situation of a ringed moon orbiting a ringed planet. It was determined that if it had a ring system, the tiny moon could have a stable moon in principle. A search of the data from the Cassini mission has failed to find such a moon, but it does tick a box in favor of moons existing in the universe. Number 9, rogue planets. At first glance, interstellar space may seem very empty other than dust and the occasional atom of hydrogen, but in reality, interstellar space also hosts an entire class of planet that sits alone from planets confined in star systems. They are rogue planets. Rogue planets typically start as members of star systems, but instabilities within those systems leads to their ejection. Indeed, it's thought by some scientists that early in the solar system's history, a Neptune-sized planet that formed here was ejected through a close encounter with Jupiter. Where that planet is now is anyone's guess. But having been ejected an estimated 4 billion years ago, it's likely very, very far away. One candidate for a free-floating rogue planet is an object known as SIP J013656.5 plus 093347. Once thought to be a brown dwarf, the size of this planet has been constrained down to 12.7 Jupiter masses, making it seem more like a massive planet than a brown dwarf, though the line is blurred. The object is particularly interesting because variations in its light curve have been interpreted as variations in cloud patterns in its atmosphere, and indeed evidence for very powerful auroras has also been found, suggesting that the planet has a very strong magnetic field. Apart from giant worlds, there should be a population of smaller rogue planets as well, including planets that might have otherwise been similar to Earth. Interestingly, the concept of a rogue planet wandering the darkness of interstellar space doesn't seem conducive to life ever arising in such a place. But with geothermal heating, such a planet could have liquid water. Who knows where life might get a foothold, though it might seem rather sad if a rogue planet is ever discovered that had evidence of life, but that life went extinct long ago when the planet froze over in the depths of space. Number 8, the antimatter fountain. The matter-antimatter reaction is the ultimate inefficiency. If you have exactly 1 gram of matter and 1 gram of antimatter and put them together, they will violently annihilate each other in a 100% conversion of mass into energy. But there's a rabbit hole here. There's no clear reason why the Big Bang wouldn't have produced equal amounts of matter